So for anybody else watching this video later, hopefully not too much later, exam 4 in chapter 6 and 7 is due this tonight at midnight. And then we're going to kick off material for exam 5, chapter 9. And I just wanted to give the viewers of the video, if you go to Brightspace, you're looking for, let's see, and get that closer. You're looking for that one, PowerPoints. You're looking for this one, review document. Okay. And work problems will look like this. Okay. Right. So, chapter 9, chemical quantities. You may recall that I introduced this material out of order. In other words, chapter 8 was for the third exam was chapter 8. And then we went back and picked up 5, 6, and 7. Now we're back on track with chapter 9, chemical quantities. All right, these are the topics that we're going to cover. We're essentially going to talk about a concept or a technique, a skill in chemistry called stoichiometry. That is, when we have a balanced equation, and everybody knows knows their symbols, they know how to write compounds, they know how to write a chemical sentence, which is an equation, a reaction. And now we're going to do something with that reaction. Once we've balanced it, then we can use it to determine if we put so much reactants into a system, then we can predict what comes out as products. And so that's our main focus in chapter 9. All right, I just mentioned that one. Recall that coefficients of a balanced equation give the relative number of molecules. They don't say anything about masses or volumes or any other relationship, just numbers. All right. So if we have this balanced equation where we're describing the combustion of ethanol, ethyl alcohol, and it produces carbon dioxide and water as products. We know that the number of atoms of each of the elements is the same on both sides of that arrow. That means it's balanced. We can speak of it in terms of molecules. We could say 1 molecule of ethanol and 3 molecules of oxygen produce 2 molecules of carbon dioxide or 3 molecules of water. That is a true statement, but it doesn't help us with stoichiometry, determining grams in, grams out. So we've got this unit of measure. I think, have we introduced this? I'm not sure if we introduced this before. I think we did. The mole. All right, the mole is just a counting number. Yeah, I know we have introduced this. All right. 1 mole of anything is this many items. It could be atoms. It could be molecules. It could be ions, right? For our purposes. And when we have 1 mole of a compound, we know how to calculate the mass of that 1 mole of compound, right? C2H5OH would be 2 carbons, right? Would be 6 hydrogens, and 1 oxygen. And each one of these is grams per mole. So when we add them together, let's see, 2402, 2, and 6.06, and 16. So this would be 46.08 grams per mole of this molecule. We have that many molecules gives you this mass. So now we have a relationship between numbers of molecules, atoms, ions, and their mass. Okay. So whenever you're presented with a chemical reaction, in whatever form it occurs, in a word problem, say you're given the names of the reactants and the names of the products, then you can write those compounds, those elements, and put them in their proper position. Then you have to balance the equation. Here's an example of copper 1 sulfide plus copper 1 oxide yields copper solid, copper metal, and sulfur dioxide gas. So when we balance it, we come out with these coefficients. A 1, of course, whenever you've got a compound or an element in a reaction, if there's no number in front of it, it's always 1. So we have 1 copper 1 sulfide, 2 copper 1 oxides yields 6 copper metal atoms, and 1 sulfur dioxide. Now we can speak of that in terms of molecules or moles. Either one works. The one that works for us when we're trying to determine input and output is moles. So the ratio would be 1 to 2 to 6 to 1. And remember that concept, because when we start making jumps from one place in a reaction to another place in a reaction, those coefficients give us a handle on conversion factors. All right, so we have, if we put in, let's see, what's the question? Also, determine how many dozen copper atoms would be produced from a dozen molecules of sulfide. A dozen molecules of the copper 1 sulfide gives you a dozen molecules of sulfur dioxide, because the ratio is 1 to 1. So for every 1 copper 1 sulfide, you get 1 sulfur dioxide. So it's 12 to 12. We have, well, if we have 6 dozen, excuse me. If we have, no, wait a minute, I'm reading that wrong. Pardon me, copper 1 oxide. Copper 1 oxide, if we put in 2 dozen copper 1 oxide, then how many moles of how many copper atoms? Okay, the ratio now is 2 to 6, or 3 times. So we would have 3, if we put in 2 dozen copper 1 oxide, we get out 6 dozen copper atoms. Let me put that on the board. I think it'll make more sense. So here's our balanced equation. Let's see, solid, solid. And we have 2 oxide, solid yields 6 copper atoms and 1 sulfur dioxide gas. There we go. Now we have a balanced equation. So if we have a dozen copper atoms could be produced from a dozen molecules of sulfide and 2 dozen of the oxide coppers. So if we start off with a dozen sulfide and 2 dozen oxides. So if we have 1 dozen of these and 2 dozen of these, we're going to have 6 dozen of those and 1 dozen of these. Right? It's just 1, 2, 6, and 1. How many moles of copper would be produced from 1 mole of sulfide? If we have 1 mole of sulfide and 2 moles of oxide. So if we have 1 mole here and 1 mole here, 2 moles there, then we're going to have 6 moles here. When you balance an equation, this ratio 1, 2, 6, and 1 is fixed. We could increase it by multiplying by a factor, say 2, 4, 12, and 2. Or we could take half of it, a half, 1, 3, and a half, but the ratio is always the same. All right, if we have this reaction where we're splitting the water molecule into its atoms. This is a decomposition. We learned that in a previous chapter. So if we take a water molecule, right, and we split it, we get a hydrogen gas and oxygen gas. That's not balanced. But if we have 2 oxygens on this side, we need 2 over here. That means 4 hydrogens. Now it's balanced. This could mean 2 molecules yields 2 molecules and 1 molecule. Or this could be 2 moles, right? 2 times 6.022 times 10 to the 23rd molecules yields 2 molecules of hydrogen, or 2 moles of hydrogen, and 1 mole of oxygen. Fixed. Since the ratio is fixed, the relationship between the two is fixed. So if I say, all right, if I start out with 10 moles of water, right, and I want to find out how many moles of oxygen would be produced, then I would have a conversion factor where moles of water would cancel, right? Numerator, denominator, and leave me with moles of oxygen. So there we have a conversion factor that's built from the coefficients. The coefficient here is 1, the coefficient there is 2. So this would be 5 moles of oxygen gas would be produced from 2 moles of water. That's what we're getting at here with the mole ratio. These ratios provide us with conversion factors. So we can determine from, say, the input of so many moles of water, we can say this is how many moles of oxygen and hydrogen we would expect as products. Okay. All right, let's take another one. Example. This is sodium, silicon, fluorine. And we're combining it with sodium metal, and it yields silicon plus there we go. All right. This equation should be balanced. Two sodiums. Wait a minute. Yeah. 2 plus 4 is 6. 6 sodium. 1 silicon. 6 fluorine. 6 fluorine. Okay. That equation is balanced. Now the question is, how many moles of sodium fluoride could be produced if 3.5 moles of sodium, 3.5 moles of sodium is reacted with excess sodium silicon fluoride? So the question is here, moles. All right. So we're starting from here of sodium, and we want to convert that to sodium fluoride. So the magic numbers, sodium has a coefficient of 4, and sodium fluoride has a coefficient of 6. Right? So the sodiums cancel, leaves us with so many moles of sodium fluoride. And I get 5.25 moles of sodium fluoride would be produced if all of that is converted to that. Okay, I got the name wrong. Sodium hexafluorosilicate. All right. That's what we know. We have a balanced equation. We're given that information. And we use this conversion factor built from the coefficients to give us that many moles of sodium fluoride. All right, let's see. Next, all right, we're going to combust propane. Propane, C3H8. Gas plus oxygen, gas. And these reactions, when they go to completion, they always produce carbon dioxide and water. Let's see. Well, it's not telling us. It could be liquid or it could be gas. Depends on the conditions. All right. So we need to balance the equation first, right? And fortunately, it's balanced already, I think. 3 carbons would be 3 over here, right? And then 4 in front of the water. And 5 in front of oxygen. There we go. So 3 carbons, yes. 8 hydrogens, yes. And 10 oxygens. So we have 6 plus 4 is 10 oxygens. That's balanced. Okay, the question is, how many moles of carbon dioxide are formed? So we want moles of carbon dioxide are formed when 3.74 moles of propane are reacted with excess oxygen. Now, why is that important? Why do we need to know that oxygen is excess? Because oxygen will not run out. There's plenty, The only thing that's going to run out is propane. It's going to be converted to carbon dioxide and water. So now we can work with that. 3.74 moles of propane. Right? Then our conversion factor is moles of propane yields moles of CO2. There we go. And the magic numbers, that's a 1, that's a 3. So let me see if I can do this in my head. 3 times 4 is 12. Carry the 1, 22, carry the 2, and 11.22 moles of CO2. That cancels, leaves us with moles of CO2. Let's see if I did it right. Yep. Well, I carried, let's see, we only need 3 significant figures, so I added 1. Should be only 3. Okay. So that's working with moles. There's one thing about stoichiometry that never changes. If you want to go anywhere in that balanced equation, from reactants to products, reactants to the other reactant, find out how much you need, or product, you have a certain amount, and you want to say how much reactant do we need to produce that much product, any of those movements must be in moles. If it's not in moles, you can't move. It's like there's a great wall between each of the reactants and products. You can't get over it or under it unless you're a mole. So first thing we do, as always, balance the equation. Then you have to convert, if you're starting with masses, you have to convert to moles. And we know how to do that because we can calculate the molar mass of each one of our reactants and products and use that as a conversion factor. Then we can convert moles of one reactor to product to moles of any of the others using their coefficients. Then if the question is, the answer must be in mass again, then you have to take the moles of the answer, the product or the reactant, convert them back to mass. All right. Get that out of my way. All right, what we've been talking about up to this point is stoichiometry. That concept was introduced at the very end of chapter 6. Now we're going to learn how to use it. In addition to what we've already introduced. And then we're going to consider the situation where you're given absolute amounts of reactants. We don't know the excess yet. We have to determine which one is excess, which one is limiting, because the limiting one will run out. And that determines the extent of the reaction. That's coming. All right. So for this reaction, chromium plus oxygen yields chromium-3 oxide. So here we have chromium, solid, plus oxygen, gas, yields chromium-3 oxide. Solid? Yeah, solid. We need to balance this equation. You can use the budget method, that's fine. And Maybe we better, right, until you get comfortable with balancing without it. So we would say chromium here, oxygen, and that's it. So we have one of these. Let's do it this way. We have one chromium and two oxygens. And over here we have two chromiums and three oxygen. Now, we've got element here, so we're going to save both of them. We got to do something. So I think we should use the cross multiply trick. Oxygen only occurs here and here. And this one has an odd subscript. This one has an even. So we take that 3 and put it here. Take that 2 and put it here. That makes 6 oxygens here and 6 oxygen there. It also changes the chromium to 4. And chromium still stays here. But if we put a 4 there, now we're balanced. Okay, that was the first step. Balance the equation. Now what are we given? What information are we given? We want to know how many grams of chromium 3 oxide can be produced. How many grams of chromium 3 oxide can be produced? If we have 15 grams of chromium, is it 1? Yeah, 1. And excess oxygen. All right. So balance the equation already. We need to know the molar masses of this element and that compound. We're going to change this one to moles so we can move from here to here. Right? Like I said, there's a great wall here. You can't get over, you can't get under unless you're a mole. So we have 15 grams of chromium. We want to convert that to moles. Right? What's the molar mass of chromium? Well, they've given it to us there, 52. Let me check to see if that's right. Yep, rounded off to 2 places is 52. Right? So grams cancel, leave us with moles. 15 divided by 52 is 0.28846 moles. Now, why did I keep so many decimal? Right? I've mentioned this before, but I'm going to say it again. I kept all these decimals so that I could avoid serious rounding errors. With the sequence of calculations, if you keep your decimals and round at the end, as long as it's all multiply divide, then you can do that. So we have this many moles of chromium. Now we want to convert to chromium 3 oxide. So this one has a coefficient of 2. This one has a 4. So we're going to take 1/2 of this, right? 2/4 is 1/2. 1/2 of that value. 1, 4, 4, 2, 3. Chromium 3 oxide. Okay? Now we know that from this many grams of chromium, we can produce that many moles of chromium 3 oxide. We want to convert it back to grams, excuse me. But we need to know the molar mass of this compound. We have 2 chromiums and 3 oxygen. So that'll give us the molar mass of chromium 3 oxide. (152) grams per mole. So now we can say, see, it's kind of busy. Let me remove that. 152 grams per mole. Oops. What's the mistake? I'm converting the wrong one. Should be down here. See, that's moles, so moles has to go on the bottom. So for each mole, we have 152 grams. Right, so 152 times that number. 152 gives us, let's see, three significant figures. 21.9 grams of chromium 3 oxide. All right. Okay. And we do our conversions. Moles of chromium first. And that gives us half that many moles for chromium 3 oxide. Then we convert back to grams of chromium 3 oxide. Now this procedure is very straightforward. It's very simple, step by step. But unless you practice it, it's going to seem like a foreign language. And it is. You're learning a foreign language in chemistry. So if you don't practice it, you're not going to be able to do these calculations with any ease, and certainly with very little anxiety. Because if you're presented with a problem like this and you've never worked those problems, all the examples that I give you, all the work reviews, all problems in the review document, and you don't practice them, you know, you're in for an anxious time during any exam. Okay. Now, this is what it looks like if we do the whole conversion in one string of conversion factors. Whichever makes sense to you. If you do dimensional analysis and follow the cancellation and creation of the units that you want, then you can do it in a single string. All right. Let's try another one. Tin-2 fluoride is added to some dental products to help prevent cavities. Tin-2 fluoride is made according to the following equation. Right? Now, is that balanced? Well, let's see. 110, 110, 2 hydrogens, 2 fluorine, 2 fluorine. That equation is balanced. Now, if you ever want to do this reaction on your own, be careful with that one, hydrofluoric acid. If it's concentrated enough, and it probably is for this reaction, then you get a drop on your hand and it'll go straight through to the other side. It won't stop. It'll go through skin, it'll go through muscle, tendons, bone, all the way through. So be careful. All right, question. How many grams of tin-2 fluoride can be made how many grams can be made from 55 grams of hydrogen fluoride. They should have said hydrofluoric acid because it's in water. Right? We have that many grams of HF and plenty of 10. Right? This is excess. Then we want to find out how much of this product can be produced. And if you're in the business of making this stuff, you definitely want to know that, right? So that you can budget the production and make a profit. Okay, first thing we have to do, convert to moles. This has to be converted to moles. All right, so grams on the bottom, moles on the top. And what's the molar mass of HF? Well, fluorine is 19. Hydrogen is 1.01, 20.01 grams per mole. All right, get rid of grams. So I'm going to do it stepwise rather than string it out into one calculation. This is 2.7486 moles of HF. Then we're going to convert it to moles of 10,2-fluoride. So HF on the bottom and SNF, 2 on the top. We have 1 and 1. So this is also equal to 2.7486 moles of 10,2-fluoride. Now we want to convert that back to grams. Right? Moles cancel. We need the molar mass of 10,2-fluoride. So we've got 2 fluorines, right? And 110, which is 118.71. 118.71. Right? So let's see, 38 and 118.71 is 156.71 grams per mole of 10,2-fluoride. We're going to multiply that times 2.7486. I get 4.3074 times 10 squared. How many significant figures can we keep? We started out with 3. That's the key. So we can have 4.31 times 10 squared. But what are our answers? Our answers are in standard notation. So we'll move the decimal 2 to the right, 431 grams of 10,2-fluoride. Oops. Mistake. What did I make? Oh. I did make a mistake. Since there's nobody in the room, nobody to catch me. There you go. That means this has to be half. So 2.7486 divided by 2 is 1.3743. And this is going to be 56.71 times 2.1537, rounded off, 2.15, 215 grams. Attention to detail. All right. One more. Let me see. How are we doing on time? We're good. We got time for another one. Okay. The following reaction appears to be balanced. Phosphorus trichloride and 3 waters yields what? Phosphorus acid. This has to be an aqueous solution, well, because that's water. This is phosphorus trichloride. It must be a solid. And this is aqueous. And it also has 3 hydrochloric acid. Okay, let's see, 3, 1, 3, and 1. Okay, good. What mass of water is needed? The mass of water is needed to complete the reaction with 20 grams of PCl3. Okay, we're not even going on that side of the equation. We just want to know how much water is needed for this reaction to proceed and use up all of the phosphorus trichloride. So what we need to do is convert grams to moles of this compound. So we got to add up 1 phosphorus, 3097, and 3 chlorines, 3545. This is 137.32 grams per mole. Okay, divided into 20. And this is 0.14565 moles of PCl3. And we want to convert that to water. So coefficient here is 1, and there's 3. So that gives us 0.43694 grams, moles of water. Now we need to convert it back to grams. Moles on the bottom, grams on the top. We've calculated the molar mass of water so many times, you ought to have it memorized. 18.02 grams times this value, and that is 7.87358 grams of water. Rounded off to 3 places, 7.87 grams. Okay. All right. Let's see. All right, we're going to do a little detective work now. Consider the reaction where X represents an unknown element. All right, so we have 6 moles of X, solid. And we're reacting it with diborane is the name of that compound, I believe. Diboron trioxide. Okay. And it produces a compound with this formula. Okay. Plus a second compound that includes that same element. Okay. So that should be balanced if I put everything up here correctly. 3, 2, 6. Okay. Question is 175 grams of X, 175 grams of X reacts with diboron trioxide to produce 2.43 moles of this compound. 2.43 moles of that compound. What's the identity of X? Well, this is an element, right? How do we identify an element? One of 2 ways. If you know the atomic number of protons, it's easy. Just look it up in the periodic table. But if you know the molar mass, you can get pretty close. And most molar masses for elements are unique. There are a couple of places in the periodic table where the molar masses of neighbors are very close together. So you would need a tiebreaker then. But let's assume that the creator of this problem is not too sneaky, and we can use molar mass. So we got the mass. What we need is moles, right? Then we can calculate molar mass and determine what the element is. Well, we have moles here with a coefficient of 1 and 6. So if we take this many moles of this compound and use our coefficients, 6 and 1, then we can find out exactly how many moles we got. 2.43 times 6, which is 145.8 of X. Okay. So the molar mass of X is equal to mass per mole, 175 grams per 145 point. No, sorry. My mistake. 14.58. There we go. And this is moles of X. So if we divide that into 175, I get 12.0027 grams per mole. Okay. So now we go to our periodic table, and as we go from left to right and top to bottom, the molar masses increase, just like the atomic numbers increase. But atomic numbers increase in whole increments. Molar masses are fractional. So we follow along until we find one that's close to this one, and the closest one to that one is carbon. Carbon 12.01 molar mass. Experimental error set this a little bit low, right? But that's the closest one, so we picked the best answer. Okay. Now, if we have see, they're going to give us an example, I do believe. We're going to talk about what is a stoichiometric mixture. If we have a chemical reaction, and let me see which one they're going to use. All right. They're going to use the Haber process. Nitrogen plus hydrogen yields ammonia. Right? Oops. Kind of dumb. There. So if we need 2 here, then that's 6 there. We need a 3 here. A stoichiometric mixture is the amount of each reactant that is equivalent to the coefficients. So a stoichiometric mixture here would be 1 mole of nitrogen and 3 moles of hydrogen. Or the ratio could tell us that maybe we have 2 moles of nitrogen and 6 moles of hydrogen. Those are both stoichiometric mixtures. Or we could have a half mole of nitrogen and 1.5 moles of hydrogen. Those are all stoichiometric mixtures. They're exactly the right amount of each one to make both of them react and disappear and produce all of it in ammonia. The artist's rendition of this reaction is, for this occasion, we'd see that the 2 big blue balls are nitrogen. So there's 1 of those, and there's 3 of the twins of the small balls. And notice that they're lined off so that each one is related to the other. 1 of these to 3 of those. If we have that exact ratio, then we get 2 ammonias for each one inside that dashed line. Okay. Suppose, rather than the stoichiometric mixture, instead, we have 1, 2, 3, 4, 5. We have 5 nitrogens. And 1, 2, 3, 4, 5, 6, 7, 8, 9. And 9 hydrogens. Okay? If we only have that many, then for each one of these, we need 3 of those, right? So if we take them one at a time, say this one needs 3 of those. Another one needs 3 more. Another one needs 3 more. Right? We've got these 2 down here, but we don't have any more hydrogen left over. We've used it all up, right? So that makes hydrogen limiting. And nitrogen is excess. Now, why would that be important? The fact of the matter is, if you know the limiting reactant, that's the one that's going to run out first. And when it runs out, the reaction stops. And you have these left over. Right? If you look in the after reaction, you see those 2 nitrogens floating around with nothing to do. And you have 2, 4, 6 of these. So this would put 1, 2, 3 times 2 is 6. So this would produce 2 for these, 2 for these, and 2 for these. That's as far as we're going. because we run out. All right. That's the concept of the limiting reactant. It's the one that runs out first. Thus, it limits the extent of the reaction's production of products. All right, calculations. Let's see what they're going to use for a reaction. In order to do a calculation to determine the outcome of a reaction, we have to know which one is limiting. And we base our future calculations on the amount of limiting reactant because it will be used up, and when it's used up, the reaction stops. Okay, here we're going to have methane and water produce hydrogen and carbon monoxide. Okay, 1 methane plus 1 water produces 3 hydrogens and a carbon monoxide. Let's see, 6 hydrogens there, 6 here, 1 carbon, 1 oxygen. We're balanced. Okay, what's the question? What is the question? Okay, we're given the equation. Okay, now what? We're saying we know the molar ratio of carbon of methane to water is 1 to 1, right? 1 to 1. So that means for every 1 mole of methane, you need 1 mole of water. And if you have that ratio, then you have a stoichiometric mixture. But in this picture, we actually have 5 methanes and 3 water. That means water will run out first because it only needs 3 of the methane to make product. And when it uses them up, when it uses itself up, the reaction stops. So this is our limiting reactant. And this is our excess. All right. So these are instructions for solving a problem. It'll make more sense when we actually use these procedure to solve a problem. Always balance the equation. Convert to moles. Convert the number of moles of each reactant to the number of moles of one of the products. If it doesn't tell you, just pick one. If the answer to the problem is in terms of how much product a given product is produced, then you go for that one. So we would take this many moles of methane, 5 moles. See, we determined the limiting reactant from this side. Now we're going to determine the limiting reactant from the product side. So this 5 moles of methane, if we use it all up, how much hydrogen will it produce? Right? Methane and hydrogen. And the ratio is 3 to 1. So this should produce 15 moles of hydrogen. Oops, not water, hydrogen. If we do the same thing for this one, right, and we convert it to hydrogen, There's 3 here and 1 there. So that's 9 moles of hydrogen would be produced. So which one is limiting? The one that produces the least amount of product. This one. This one is limiting. Okay? If we do it this way, and the question is how much hydrogen is produced, we've already gone this step to here, then we can just finish the reaction with this information and throw that one out. Okay, that's what I've just done. Then if your problem asks for it, convert it back to some other unit. All right, so here we have an example where we're combusting aluminum in oxygen. That's going to be a very exothermic reaction. So if we have 4 aluminum plus 3 oxygen, and we're leaving off the phases for now. Okay, there's our reaction. You react 10 grams of aluminum and 10 grams of oxygen. What mass of product will be produced given that the molar mass of aluminum is and oxygen is and aluminum oxide is? So they're giving you the molar masses already. All right. Can we say anything about the limiting reactant yet? No. Because these reactions are not based upon mass, they're based upon moles. So what we're going to do is convert this to moles and this to moles. First, 10 grams of aluminum, convert it to moles. So what does the aluminum weigh? 2698. All right. Moles of aluminum. 10 divided by 2698 is 0.37064 moles of aluminum. And since we're already here, let's go ahead and find out if we use all of this, how much of that will we produce? Oops, Al2O3. Ratio is 2 of these, 4 of those. So to produce half that much. 0.18532 moles of aluminum oxide. Okay. Now let's do the same thing for oxygen. 10 grams of oxygen is 32, 1 mole. So we divide 10 by 32. And that's 0.3125 moles of oxygen. Then we're going to convert this to product. So oxygen on the bottom, aluminum oxide on the top. So this is still 2. This one, though, is 3. So we'll take 2/3 of that value, which is 0.20833 moles of oxide. All right. Now we can decide which one is limiting. Right? The least amount that's produced from the given reactants is aluminum. This is limiting. This is excess. Okay? So now that we know what the limiting one is here, we can convert that to mass. All we need is the molar mass of aluminum oxide, which is given there, 101.96. Okay. Flip that one in 101.96 times. And that's 18.89548 grams. And we've got three significant figures. So it's 18.9 grams of aluminum oxide. That's all that we can produce from the amount of reactants that are given. All right, so there's your balanced equation. We converted moles of aluminum, moles of oxygen. Okay, now we're going to convert each one to product. Right? Aluminum gives you 0.853. Oxygen gives you 0.2083. So we know which one is limiting now. And we take the limiting amount and proceed with the rest of the calculations. Gives us 18.9 grams of aluminum oxide. And what's left over? Well, if we want to find out what's left over, what do we do? Right? Let's see. Is that part of the problem? No, but I'm going to do it anyway. We know how many moles we started with, right? So if we say we want to convert this many moles into this many moles, see how many moles of oxygen that we need to use, right? So if we're going to use aluminum here, we're going to use up all of this. Moles of aluminum. And we want moles of oxygen. How much oxygen is required of that excess? So the ratio here is 4 and 3. So we'll take 0.37064 and divide by 4 and multiply by 3. So this is required. 0.27798 moles of oxygen required. Okay? How much do we have of oxygen? Okay. We have 0.3125. So we didn't use it all up, right? We knew that in advance. 0.3125 oxygen minus 0.27789. Okay? So let's do 0.3125. Yep. And let's subtract. This is 0.03452. So let's see. This goes down like that. And we can use 1, 2, 3, 4 here. So 0.0345 moles. Oxygen excess. Right? So how many grams do we have left over? Well, 0.0345 moles grams, 32 grams per mole. And I get 1.10 grams excess oxygen. Okay? We know that we're going to have that much oxygen left over. All right. Yeah. All right. Which of the following reaction mixtures could produce the greatest amount of product? For combusting hydrogen and oxygen to make water. All right. Let's clear the board. With this equation, 2H2 plus O2 yields 2H2O. If we have 2 moles of hydrogen and 2 moles of oxygen, right? 2 moles and 2 moles, right? How much water can we produce? All right. With this many, we have 2 here. We only need 1 there. So this 2 will produce 2 of these. And this will be excess. All right, we'll have a mole left over. B, 2 and 3. Similar situation, only now we have more oxygen left over. We can still only produce 2 moles of water. C, let's see, this is A, B, C, D, and E. So C says 2 moles of hydrogen and 1 mole of oxygen. That is a stoichiometric mixture. 2, 1, 2. Okay. And D, now this doesn't mean that these are all here at the same time. These react to produce that. That yields that. All right. And then D says 3 and 1. Now, we're going to use all of this up because we only need 2 of these. That means oxygen is limiting this time. But it still produces, 1 produces 2. Okay? E says each produces the same amount. That is true. There you go. Oh, Haber again. Fritz Haber. Making ammonia out of nitrogen gas and hydrogen gas. Okay. How many grams of ammonia can be produced from the mixture of 3 grams each of nitrogen and hydrogen? All right. N2, 3H2 yields 2NH3. We have 3 grams each. 3 grams here, 3 grams here. I'm going to move it down here so we can do calculation straight across. How many grams of this can be produced? All right. Which one is limiting? How many moles of nitrogen do we have? Well, this is 28.02. Look it up. 2 times 14.01 equals 0.10707 moles of nitrogen. Now we want to convert to ammonia, right? So we have 1 here, 2 there. That makes 0.21413 moles of ammonia. Now we'll do the same thing with hydrogen. All right. So we have grams here, moles there, and this is 2.02. 3 enter 2.02 divide. This is 1.4851 moles of hydrogen converted to ammonia. So we have 2 ammonia for every 3 hydrogen. And we get 0.9901 moles of ammonia. Okay, so nitrogen is limiting. Hydrogen is excess. Okay, and the question is, how many grams of ammonia can be produced? Well, now we have the moles of ammonia, 21413. We'll just convert that, excuse me, we'll convert that to grams. So ammonia is going to be 14.01 for nitrogen, 3.03 for the hydrogens, 1704. And this is 3.64882 grams of ammonia. We'll round it off to 2 places. No, 3. Sorry, 3. 3 places. 3.65 grams of ammonia. Okay, found out which one was limiting, and we use that to calculate the rest of the way. 3.65 grams. Okay. All right. That takes care of limiting reactants. That's the limiting reactant is one factor that affects the total outcome, the total amount of product that you can get. Another, many other factors lumped together in yield. Other factors that can decrease the amount of product that you get, right? Such thing as spillage, side reactions, reactions that you don't want, that don't produce your product, but they take your reactants and send them someplace else, right? Those will ruin your yield. The fact that all of your reactants don't go to product, right? We may set up an equilibrium situation, which we haven't, we sort of touched on it, but we haven't delved into it quantitatively. But there are many factors that can reduce the amount of yield of your product. And this is that discussion, percent yield. It addresses mathematically the problem of efficiency in any laboratory or any industrial reaction. Theoretical yield. That's what we've been working with up to now. The theoretical yield is the maximum amount that you can expect from a reaction. If all of the limiting reactant is converted to product, then that is 100%. That's the theoretical yield. The actual yield is what's measured. So somebody has to measure the output. What do you get after this reaction? And then we ratio the two. Percent yield is simply actual divided by theoretical times 100. That's percent yield. Now the yield can be in mass, and that's that's probably as far as we're going to go. It could be in volume if they're under the same conditions, gaseous products under the same conditions, or liquids could be volume liquids, right? So if we have, what's the percent yield of the product? Sulfur trioxide. If 1.5 grams of sulfur trioxide is produced from 1 gram of oxygen and excess sulfur. So here's our balanced equation. Okay, and we have 1.5 grams of sulfur trioxide. And 1.5 grams is produced. So this is actual. Okay. And if we start with 1 gram of oxygen, and this is excess, and we convert it all to sulfur trioxide, how much theoretical will we get? Right, we've done that before. We just need to convert this to moles. One divided by 32. And I get 3.125 times 10 to the minus 2 moles of oxygen. Then we'll convert this to sulfur trioxide. So this is 3, and this is 2. And that gives us 2.0833 times 10 to the minus 2 moles of sulfur trioxide. Then we want to convert this back to grams so we can compare it with the actual amount. So sulfur trioxide should be 32.07 for sulfur, and then 3 times 16. That's 8007 times that value. And that gives us 1.67 rounded off grams sulfur trioxide theoretical. So, calculate the percent yield. It's 1.5 grams divided by 1.67 grams times 100. Which is 89.8%. Which is pretty good yield, actually. There's all our calculations in sequence. Now we can compare the actual with the theoretical. And I will point out, this is a dimensionless number. It simply means parts per 100. So if you're going to do it this way, well, you have to know how the percent yield was calculated. Let's put it that way. In order to say it's 89.8 grams per 100 grams expected. If we expect 100 grams from the reaction, we're only going to get about 89.8%. 89.8 grams out of that 100. Okay. Now, one last problem. Yeah, one last problem. And we'll be done with this chapter. So we're working with a reaction where P4 is reacted with fluorine gas. So we have P4 solid reacting with fluorine gas, and it produces phosphorus trifluoride gas. Okay, what mass of P4 is needed to produce 85 grams actual of phosphorus trifluoride if the reaction has 64.9% yield? Right? So instead of going this way now, we're going to work backwards because we want to find out grams. Right? In order to get from this side to that side, we have to have moles. But we want to know what is the theoretical amount so that we can say we need that much here because we're going to lose some. Right? We want the theoretical amount here. We're given 85 grams of PF3 is our actual. Right? So if we go back to our formula, percent yield equals what? 64.9%. 64.9%. And that's equal to theoretical mass. And this is 85. Oh, excuse me. I got it upside down. Actual on top, 85 grams. And this is theoretical. PF3. Right? So, times 100. Right? So if we bring the 100 over here, that divides into this and makes it 0.649 equals 85 grams over theoretical PF3. Okay? So if we bring this one over here and this one over here, then we get the theoretical PF3 equals 85 grams divided by 0.649. And that's 130.97 grams. So that's our starting point. Let's go, put it over here. 130.97 grams PF3. We need to convert that to moles so we can work backwards. So what's the molar mass of PF3? Well, phosphorus is 30.97 and 3 times 19 for fluorine. Which is 87.97. We divide that into 130.97 and we get 1.489 moles of PF3. So now we can convert this to phosphorus. Right? There's one of these and 4 of those. So 4 divided into that value is 0.3722 moles of P4. Now we just convert moles of P4 back to grams. So phosphorus is 3097, right? 3097 times 4, which is 123.88. And there. So I get 46.1 grams of P4 is required. Yeah, let's see if I made a mistake. Okay, that looks good. That looks good. We're stringing our calculations together. 46.1. All that means is we need 46.1 grams of P4 in order to produce 85 grams of product under real conditions, not theoretical, under real conditions. That should be the last one. Yep, that's the last slide. Okay, so this is Tuesday. We're going to meet Thursday for let's see, Tuesday, Thursday. We're going to meet Thursday for review of this material. And I'm going to work from the review document as always. Pick out a few of those problems, work them out, and then you'll have spring break to study for the next exam, which we'll have on the first day back, Tuesday that we come back. You'll have an exam on this material. And just as a reminder, I have to turn in midterm grades this coming Monday, a week from yesterday. It's coming Monday, I turn in the grades. So if you've got anything that's missing, you better go into Brightspace and check your grades and see if you got any missing assignments or exams and get them done. Right? Get them done before midnight Saturday. So I'll have a day to compile the grades. And actually not just compile, but grade any submitted work. All right. So that's it for today. And I'll see you on Thursday for a review of Chapter 9.